Okay, thanks for the introduction. Hello everyone, welcome to my talk, Sharp Statistical Guarantees for Adversarially Robust Gaussian Classification. This is based on our ICML paper with the same title. This is joint work with Yuting Wei from University of Pennsylvania and my advisor, Pradeep Ravikumar. So as mentioned by Xiaojie, please feel free to ask any question in the chat during the talk. Okay, so what will be the topics of this talk? Actually, it will be connecting two seemingly irrelevant fields. So the first of all, we have the statistical minimax theory, which is a very old field dated back to a few decades back. And on the other side, we have the adversarial example, which is a very new field. Actually, it's introduced in a famous paper by Goodfellow et al. In 2014. And we hope that we can use our tools from this classical statistical theory to help us understand the challenges in adversarial examples. First of all, let's talk about what are the adversarial examples. So in this famous paper by Goodfellow et al., the authors found that it is possible to add some tiny noise to the input image, which makes the deep neural networks classifying an incorrect result. For example, we have a panda picture here. After adding some very, very tiny noise, which is almost imperceptible to humans, the deep neural network will instead classify the picture as a gibbon with extremely high confidence. So why is this problem very important? Well, as we all know, deep learning has been applied to many real-world applications. For example, let's say we are creating an adversarial example to a stop sign for a self-driving car. Originally, the stop sign was classified correctly, but after adding some tiny noise, it was classified as max speed 100 miles per hour. So this will cause a huge problem because this will make the self-driving car thinking it's safe to drive and cause some serious trouble and put people's life in danger. And furthermore, this isn't just an hypothetical situation. And group from Berkeley created some physical real-world adversarial examples on stop signs. And you can see that when using the most famous and most popular object detection algorithm then called FastRCNN, the object detection algorithm completely ignored the existence of the stop sign. So it is indeed a real problem for adversarial attacks in self-driving cars. So given these examples, I hope I have convinced you that adversarial example is indeed a very important problem for machine learning. So in order to get some theoretical understanding of this problem, we first need to define mathematically what adversarial examples are. So let's start with the classical standard classification, which there's no adversary. So in the standard setting of classification, the learner wants to output a classifier called F, and he wants to minimize some loss function called L. So here, the F is a classifier, as we mentioned, and the loss function here we choose the 0-1 loss, which is 1 whenever y does not equal to y prime and 0 otherwise. And in the robust classification problem, instead, we have a two-player game. It's a game between the defender and the attacker. The defender is very similar to the previous standard classification setting. He wants to output the classifier F and tries to minimize the error. The attacker instead, he wants to make the things worse. He tries to maximize error and by adding a perturbation to the input image. So put it mathematically, we are looking at this minimax game between the defender and the attacker. So here, the adversary can add a perturbation inside this perturbation set called capital delta. the most commonly used perturbation set is the L infinity ball, for example. And we may choose some other perturbation set like L1 or other LP perturbation. So to put it in an equivalent way, we can write this loss function as a robust 0-1 loss. So so whenever the adversary is possible to flip the decision of the classifier, we count the classification result as an error. So to help understand the robust classification setting, we first look at a toy example. This is a two-dimensional data set. This figure is from a paper by Hongyang Zhang. And so here we have a binary classification problem between the blue dots and the yellow dots. So on the left-hand side and right-hand side, we have two slightly different classifiers with different decision boundaries. So here is one of them, and here is the other of them. So the adversary here can perturb each input sample within each box around it. So here is one of the boxes, and here's the other, and here's the other. And as you can see here, both of the classifiers correctly classified every input here. Like they made 100% accuracy in a standard sense. However, the left-hand side, the classifier on the left-hand side is not robust. This is because that when the adversary perturbs the input data here from here, it flips the decision of the classifier. Therefore, it makes an adversary example here. And the same story for this example and this example and this example. But in the contrary, on the right-hand side, the classifier classified everything correctly and robustly. That is, every box around the input data is inside the decision boundary. So it has been many years since the original adversarial example paper around 2014, but this problem is still far from being fully resolved. There are a few key challenges. I will mention them one by one. So first of all, there is the challenge from optimization. Training the robust classifier can involve some optimization problem, which is minimax and non-convex, non-concave, non-convex, non-concave. Very, very challenging to solve in the optimization sense. And second, to correctly evaluate the performance of the classifier, we need to find the best response for the adversary. This is also challenging because it also involves this challenging non-convex optimization problem, and it makes many proposed defense algorithms broken later by other stronger attacks. And finally, we are going to talk about the generalization issue, which is the focus of this work. The generalization issue is about the sample complexity of learning a robust classifier. This is also challenging, and we'll talk about why this is the case. So here is a figure from a paper from 2018 by Schmidt et al. They show that for the most popular adversarial training algorithm, we can see the plot of the training and testing error in the adversarial setting, as well as the test error for the standard setting. We can see that the orange line is the adversarial test error, and the blue line is the adversarial training error, training accuracy, sorry. So we can see that the training accuracy is around 90% or even close to 100%. But test accuracy in the robust setting is only around 50%. So this gives us about 40% of generalization gap. In contrast, in the standard setting, the generalization gap is only around 10%, which means like 100% accuracy in training and 90% accuracy in testing. So the generalization gap in the robust setting is significantly larger than the standard setting. So this gives the conclusion of Schmidt et al. as robust generalization requires more data. So in short, the key question in the generalization issue of adversarial robust learning is the following. How many samples do we need to learn an adversarially robust classifier? To put it in a mathematical way, assuming that we have access to n IID samples from the underlying distribution, how small is the difference between the test accuracy of the learned classifier f hat n and the minimal possible robust accuracy among, the robust error among all possible classifiers? This is the difference between the two terms. Well, providing an answer to this question might be difficult in general. Like for deep neural networks, it's a very challenging problem. We may focus on some simpler and tractable models. This brings us to the conditional Gaussian model here, which is one of the most fundamental models in the statistical learning. In a conditional Gaussian model, we are looking at a binary classification problem. Here we have some blue dots and yellow and red dots. So the blue points are following a Gaussian distribution with mean mu and sigma and covariance sigma. And for the red points, it's following a different Gaussian distribution with mean negative mu and covariance also sigma. And there are roughly the same blue points and red points. And the goal is to do a robust classification in this for this distribution with unknown value of mu and sigma. And also we want to specify that the adversary can perturb each sample around themselves in a bounded norm bar. So here the perturbation set is denoted by capital delta, and is defined as delta for which the B norm is bounded by epsilon. So the B norm can be almost any norm induced by a convex set. For example, any LP norm for P is P larger than 1 falls into this category. The conditional Gaussian model is a very classical model and has been studied extensively in standard classification. In fact, when epsilon is 0, that is in the standard classification, the problem reduces to Fisher's LDA, which has been introduced in the 1936 paper by Ronald Fisher. So it is indeed a very, very old problem. So before going to our results, let's discuss some prior works that motivates our work. There have been several attempts to understand the generalization properties of adversarially robust classification. For example, there is this paper by Kim and Law in 2018, and Ng et al. In 2019, and Awasi et al. In 2020. All of these results are based on an argument called uniform convergence. So basically, what the results are saying is that they consider a family of classification rules denoted by capital F, and show that the empirical error, the training error, and testing error are close for all of the classifiers among F, and the difference is in the order of 1 over square root of n. If we assume that the optimal robust classifier is indeed in capital F, this gives us a roughly square root of d over n convergence, where d is the input dimension. In a concurrent work of Dobreva et al., they consider the same Gaussian setting with ours, and they also use the uniform convergence argument to give an square root of d over n rate. We know that this rate is also very common in the standard learning setting. But in the robust setting, there is no existing lower bound on the rate of convergence for the Gaussian setting. And the natural question here is whether the square root of d over n rate is optimal. And can we improve it, or can we prove it a lower bound of the same square root of d over n? And in this talk, we'll be using the tools from the classical statistical minimax theory to understand the generalization or sample complexity issue in adversarial examples. So here are some of our contributions. So the first of all, we are the first paper to try to understand the sample complexity issues through the lens of statistical minimax theory. We introduce a notion called adversarial signal-to-noise ratio, which helps us understand and explain why robust classification requires more data. In terms of theoretical results, we prove a near optimal upper and lower bound on the minimax risk. Of course, it's a minimax robust classification risk with nearly minimal assumptions. And it turns out that the square root of d over n rate is not optimal. And we can prove a much better d over n fast rate in robust classification. This is also the first so-called fast rate in robust classification, to our best knowledge. Okay, so now we are ready to talk about our results. To set the stage, we just want to recall that our goal is to analyze the following statistical minimax error for robust classification under the Gaussian conditional model assumption. So here, we want to analyze the difference between our learned classifier, the error of our learned classifier, and the minimal possible error among all of the possible classifiers. And f hat n is a classifier which is based on NIID samples from a conditional Gaussian model. And we want to measure the performance of our classifier using a worst case performance measure, which means we will measure the performance among a class of possible distributions, which we'll specify later. So recall that, as we mentioned earlier, in a standard classification setting, which means there is no adversary, the problem reduces to Fisher's LDA. And this is indeed a very, very old problem starting from 1936. And it is very natural to ask, what do we know about it, and set it as a starting point of our analysis. So it turns out that in the Fisher's LDA's problem, there is a very crucial quantity called signal-to-noise ratio, which plays a very important role. So the signal-to-noise ratio measures the normalized distance between the two means of the Gaussians. So mathematically, it's the Mahalanobis distance between the two Gaussian means, which is equivalent written as 2 times square root of mu transpose sigma inverse times mu. So you may ask, why is it called signal-to-noise ratio? This is because in the one-dimensional setting, the signal-to-noise ratio can be written as the ratio between the two terms. The first term is the difference between mu and the negative mu, which we call signal because it's the difference between the means of the distribution. And the other term is the noise, which is the standard deviation of the Gaussian distributions. So this is exactly the name of signal versus noise. So in the Fisher's LDA's problem, it turns out that the smallest classification error, R star, is a function of the signal-to-noise ratio. So here, the phi function is the Gaussian tail probability. Phi of C is the probability that a standard normal variable is larger than C. And the smallest classification error is phi of half signal-to-noise ratio. And this smallest classification error is achieved by a linear classifier, which is sine of sigma inverse times mu transpose times x. This is also known as the Fisher's linear discriminant. So in summary, the signal-to-noise ratio, this notion measures the hardness of classification because the minimal classification error depends on signal-to-noise ratio. So now we are ready to talk about the main results for the Fisher's LDA. Actually, these are existing results. So this let's talk about the minimax rate. Let's consider the family of distributions, the family of conditional Gaussian distributions with a given signal-to-noise ratio. That is, we assume that we know that the signal-to-noise ratio is exactly R. It turns out that by the minimax rate is given in the following form. This is d over n times an inverse exponential factor in R squared. This result is first given by Li et al. In AI Stats 2017, but they only give a optimal lower bound. And in the later result by Cai and Zhang, they also complemented with a nearly matching upper bound. So to put it in a different way, to achieve an error of R star plus epsilon, we need roughly d over epsilon times e to the minus 1/8 R squared samples. So basically, if the signal-to-noise ratio gets larger, we need a smaller number of samples. Okay, so this is all we know about the Fisher's LDA. That is the conditional Gaussian model in the standard classification setting. And next, we will move on to the robust classification setting. And the first question here is, what can go wrong in the robust setting? First of all, as we can see earlier, the signal-to-noise ratio exactly characterizes the hardness of the standard classification problem in the Gaussian setting. But is it still the case in the robust setting? Or can we find a similar quantity that plays a similar role in the robust setting? It turns out that signal-to-noise ratio is no longer the correct answer. This is because that we can find a counterexample which involves two different distributions, P and P prime. They have the same signal-to-noise ratio. Actually, it's 12 constant signal-to-noise ratio here, so that they have they have the same smallest classification error. They are both very small, 10 to the negative 8. But they have very different behavior in the robust setting. For one of the distributions, it's also possible to find a robust classifier which has a robust error of 10 to the negative 8. Also extremely small. But for the other distributions, it is just impossible to find any classifier that achieves a robust error less than 50%. We also want to recall that a trivial classifier which always output one of the classes also achieve an error of 50%. So the 50% is just a meaningless error. So let's go through this counterexample. So first of all, we need to find an example where it is indeed possible to find a robust classifier. So here is the setting of the parameters. Our setting is very simple. We just set the covariance matrix to be identity. And we are considering the most standard perturbation, L infinity perturbation. And this perturbation is bounded by 6 over square root of d. And we assume the dimensionality is very large. And the parameter mu, which is the mean of the Gaussians, is set to the following value. It has the first coordinate to be 6, and all of the remaining coordinates to be 0. As we mentioned earlier, the signal-to-noise ratio is 12, and R star, which is a minimal classification error, is 10 to the negative 8. To find a robust classifier, we just need a very, very simple rule. It is just outputting the sign of the first coordinate. And we can show that the robust classification error of this simple classifier is roughly 10 to the negative 8, extremely small. Okay, so now let's move on to the other example where it's impossible to find a robust classifier. Actually, this example is very, very similar to the previous example. It shares many common parameters with the previous examples. For example, the covariance, the perturbation. The only difference is that the parameter mu has a different form. It has all of the coordinates to be the same, which is 6 over square root of d. We can also show that the signal-to-noise ratio is 12, and in the standard setting, it has the smallest classification error of 10 to the negative 8. However, in this case, there's no robust classifier. It's not immediately obvious that why is this the case. That is why there's no robust classifier in this setting. And we will try to prove this argument. So to prove this argument, we need a concept called the universal adversary. This is introduced in a paper by Musavi Desfuli et al. In CVPR 2017. They empirically show that a substantially weaker adversary can fool the deep neural networks. That is, it only outputs an image agnostic adversarial perturbation. That is, for all different x, it outputs the same adversarial perturbation. So to put it in a mathematical way, the adversary is in a very special form. He first chooses a perturbation z, which satisfies this bounded norm constraint. And for any test data from the first class, it perturbs x prime to x minus z. And for any test data with the second class, which is y equal to -1, it perturbs in the opposite direction. Now, it makes this problem even simpler by telling the learner the value of delta. Now, because the conditional distribution of x given y is a Gaussian distribution, as we assumed by the conditional Gaussian model, we can see that this universal adversary, in fact, turns the problem into an equivalent problem of standard classification with a slightly perturbed Gaussians. Actually, the mean parameters are mu minus z and negative mu minus z, and the covariance ratio remains the same as sigma. So let's come back to the second example where we want to show the robust classifier does not exist. Recall that the mean parameter is set as 6 over square root d across all possible dimensions. And the universal adversary here just chooses the z, the perturbation to the mean parameter, as the same as mu. Recall that the universal adversary turns the problem into a standard classification with perturbed Gaussians, and the mean parameter is mu minus z and negative mu minus z. So if we plug in the relation z equals mu here, this makes the problem of classifying two identical Gaussians, that is n0i versus n0i. And it is clearly impossible that to have an error any better than 0.5. So now that we proved that the signal-to-noise ratio is not a proper measure for the hardness in the adversarial setting, to fix the problem, we will introduce a modified notion of signal-to-noise ratio, for which we call it adversarial signal-to-noise ratio. Actually, this is closely related to the previous notion of universal adversary. It is actually the smallest possible signal-to-noise ratio when we apply a universal adversary to the distribution. And actually, in the previous example, one of the distributions has a adversarial signal-to-noise ratio of 12, and the other distribution have an adversarial signal-to-noise ratio as 0. So they have different adversarial signal-to-noise ratios, and their difficulties are different. Using a result from Bagogi et al., we can show that the minimal robust classification error is, again, a function of the adversarial signal-to-noise ratio. This shows that the adversarial signal-to-noise ratio is a proper measure for the hardness of the robust classification, because the minimal error is a function of the adversarial signal-to-noise ratio. Now, having defined this adversarial signal-to-noise ratio, we are now ready to formally state our results. So let's consider the family of distributions with a fixed adversarial signal-to-noise ratio. That is, the adversarial. We assume that the adversarial signal-to-noise ratio of our input distribution equals to R. Now, the main result of our paper is that we show that the minimax robust excess risk scales also in this form, d over n times an exponential factor, inverse exponential factor in R squared. And we also show that there is a computational efficient estimator that achieves this minimax rate. As you can see, this is very, very similar to the existing result in Fisher LDA from Li et al. In 2017. The only difference is here we need to replace the standard risk by robust risk, and the standard signal-to-noise ratio by the adversarial signal-to-noise ratio. And as we can see from the rate, the convergence rate here is d over n instead of square root of d over n by the uniform convergence approach. It's also worth noting that the prefactor here, e to the minus 1 over a times r squared, is also very sharp. So what can we learn from this minimax risk result? So first of all, we can compare the minimax convergence rate in the standard and adversarial robust setting. As we mentioned earlier, the only difference between the standard and the adversarial setting in terms of minimax convergence rate is we need to replace the signal-to-noise ratio by the adversarial signal-to-noise ratio. The first observation here we can make is that the adversarial signal-to-noise ratio is always smaller than the signal-to-noise ratio. In other words, the adversarially robust risk is always converging slower than compared to the standard risk. However, it is unclear that how many times slower is the convergence compared to the standard setting. And this is a non-trivial problem. Here, we provide a concrete example. Again, we consider the simple setting where the Gaussians have an identical covariance with an L infinity perturbation set. And we choose the mean parameter mu to be 1 plus epsilon and in the first coordinate and epsilon on the other remaining coordinates. We can show that depending on the different value of epsilon, the difference between adversarial signal-to-noise ratio and the standard signal-to-noise ratio can be very different. For example, if epsilon is very small, it's smaller than 1 over square root of d. Both the adversarial signal-to-noise ratio and the signal-to-noise ratio are constants. When the perturbation epsilon is slightly larger, which is the log factor times square root of d, we can show that the adversarial signal-to-noise ratio is still a constant 1, but the signal-to-noise ratio, the standard signal-to-noise ratio, is a poly log d. And when epsilon gets larger, in fact, when epsilon gets to a constant level, theta 1, we can show that adversarial signal-to-noise ratio is still 1, but the signal-to-noise ratio is much larger. It's order of square root of d. And combining these three different cases, we can compare the rates of convergence between the standard setting and the adversarially robust setting. So here are the three cases. In the first case, both of them are in the order of 1, and the convergence is only a constant time slower. In the second scenario, it's poly d times slower. And in the third scenario, it's exponential of d times slower. So from this example, we can see that the adversarially robust classification requires more data in some sense because the adversarial perturbation can decrease the signal-to-noise ratio. Because on the right-hand side, the signal-to-noise ratio can be ranged from 1 to square root d. But on the left-hand side, this adversarial signal-to-noise ratio is always constant. So next, we will describe what our estimator is. That is the estimator we use to achieve this minimax risk. So our estimator is heavily inspired by this paper by Bagogi et al. Published in Europe's 2019. They established a analog of Bayes optimal classifier in the robust setting. To be very concrete, they show that a linear classifier in a very special form has the minimal robust classification error. This linear classifier has the following form. It is very similar to Fisher's linear discriminant, except that you will need to perturb the mean parameter by a shift of z naught, and z naught is defined by the minimizer of this quadratic form under the bounded norm constraint. This is also quite relevant to the universal adversarial perturbation mentioned earlier. So, but instead, in order to use this robust Bayes optimal classifier, we need to know the exact value of these population quantities mu and sigma. I will also want to mention that the proof of this result is very non-trivial. It is based on some arguments based on optimal transport, and it's beyond the scope of this talk. So in order to make this this classifier an empirical estimatable estimator, we just need to replace these population quantities by their empirical estimates. That is, we use the empirical mean and empirical covariance in place of mu and sigma, the population counterpart of them. And we would like to mention that this this estimator is polynomial time solvable because this is a convex program under a convex constraint, and it's a minimizing problem. And this efficient estimator is actually achieving the minimax rate. And we will cover the proof later in the talk. So if you are familiar with the previous paper by Schmidt et al., you may ask, what's the difference between our paper and their paper? So here we provide a brief comparison with their results. In the paper by Schmidt et al., they also studied the conditional Gaussian model. Actually, they analyzed a very specific regime where they chose the sigma to be a diagonal matrix and mu to be in the scale of square root d and sigma to be in the order of d to the 1/4. And they consider the adversarial perturbation to be a L infinity perturbation. So they show that in order to get a 1% standard classification error, you only need a constant number of samples. But in order to get a robust classification error slightly better than a half, you need at least square root d samples. This shows a separation between the sample complexity in the standard setting and the robust setting. However, their results are weaker than ours because, first of all, their analysis does not provide a statistical rate of convergence. That is, they do not provide a convergence rate when n grows much larger than square root d, for example. And second, our analysis is able to handle other regimes. That is, we can set these sigma, mu, and the perturbation to be much more general. These can be arbitrary numbers, almost arbitrary numbers, and we can consider other forms of perturbations, like other LP perturbations. We can also compare their estimator with our estimator in experiments. Here, we plot the excess risk versus the number of samples. As you can see, Schmidt et al.'s estimator has an excess risk saturated at a level strictly above 0, while our estimator's excess risk converts to 0 in a rate proportional to 1/n. This is also a very crucial difference between our estimators and analysis. So next, we will talk about the proof of the convergence upper bound. So recall the goal here is to analyze the difference between the learned classifier, which is a linear classifier, W has 0, the error of this classifier against the optimal robust classifier, W0. And it turns out that because both of these classifiers are linear, we can write a robust classification error for linear classifiers in a closed form, which also involves this Gaussian tail probability function and some linear fractional form about the parameter W. Now, plugging this closed form classification error, we can get a difference between some two nonlinear functions. And the first step of the analysis is to use a first order approximation of this nonlinear function. By Taylor expansion, we can guess this difference is roughly this e to the minus 1/8 adversarial signal-to-noise ratio square times a delta n, for which delta n is the difference between the two arguments inside. So you can already see that this is already very close to the minimax bound we proved, in the sense that the first prefactor is already the same. And the remaining work is just to analyze the delta n, actually the magnitude of delta n. And after a lot of algebra, we can actually decompose the delta n into 4 terms. Most of them are very complicated, and I will skip the exact expression for them. But it is necessary to do the analysis in such a complicated way, because if you're not careful, you will get a weaker convergence rate of square root d/n instead of the fast rate d/n. And I will only focus on the main term here, which is a sum, which is essentially the norm of a vector, which is sum of 2 terms. And we only need to show that this T4 factor is growing in the scale of d/n. And this is very simple because we only need to use some standard results for the concentration of empirical mean and empirical covariance. So standard statistical theory tells us that the mean parameter converges in a rate of d/n, square root d/n, and as well as the operator norm of the difference between the empirical covariance operator and the population covariance operator. This the operator norm is also scaling at square root d/n rate. So plugging these 2 results, we can show that by triangle inequality, the T4 factor is upper bounded by the sum of these 2 terms. And both of these 2 terms are in a square of this square root d/n rate, which is d/n. And after establishing this step, we have completed this upper bound proof. So the next goal of this talk is to briefly go through the proof of this lower bound. In fact, the main idea behind the lower bound proof is closely related to the universal adversary introduced earlier in this talk. We want to use a black box reduction argument that shows that robust classification is in some sense harder than standard classification. To be very precise, the term harder here means that for any distribution P with certain amount of signal-to-noise ratio, this is a standard signal-to-noise ratio R, we can find a different distribution P prime with adversarial signal-to-noise ratio R. And we compare the standard risk and adversarial risk of any classifier under these two different distributions. And we can show that under distribution P prime, the robust access risk is always larger than the standard access risk measured in the distribution P. If we take minimax over F and distribution P on both sides, this shows us the minimax robust access risk is lower bounded by the minimax standard access risk over this distribution class. And the quantity on the right-hand side is exactly what has been established in Li et al.'s paper. And now we get the minimax lower bound for the robust access risk. So this completes the proof of the lower bound. In summary, we provided the first statistical minimax optimality results for the adversarially robust classification. And we introduced the notion of adversarial signal-to-noise ratio, which characterizes the hardness of the adversarial robust Gaussian classification and partially explains why adversarial robust classification is harder than standard Gaussian classification. We provided the first matching upper and lower bounds for minimax access risk and provided an efficient minimax optimal algorithm that achieved this fast OD of n rate. And the reason behind why adversarial robust classification requires more data is just because the perturbation decreases the signal-to-noise ratio. So it has been 1 year after we released the paper on arXiv, and there has been many follow-up works. First of all, our analysis implicitly assumed that n must be slightly larger than d in order to get the access risk converging to 0. And there has been several papers analyzing the conditional Gaussian model in a proportional regime, that is n is linear in d. These include Javamart et al. And Tahiri et al. They almost appeared at the same time on arXiv in the October last year. And there has been also some attempts to extend this minimax type analysis to other statistical learning, robust statistical learning problems. For example, this paper by Xin et al. In AI Stats 2021, they analyzed the minimax risk for adversarially robust Gauss linear regression problem. And there is also another paper from a group from UCSD by Bhattacharjee et al. In ICML this year. They analyzed the sample complexity for large margin classification. Finally, I want to mention a few future directions for after this work. The first future direction is applying this minimax type analysis to add other adversarially robust learning problems. Of course, as we mentioned earlier, these papers by Xin et al. And Bhattacharjee et al. Already extends our analysis to the problem of linear regression and large margin classification. An interesting problem here, open problem here, is that what about the quadratic discriminant problem? This is very, very similar to the Gaussian classification problem, except that this allows the covariance matrices between the two conditional distributions to be different. In the standard setting, we know that the optimal classifier is a quadratic classifier. But in the robust setting, it is very non-trivial to prove what's the exact form of optimal robust classifier, and it remains an open problem. The other problem is the non-parametric classification. In fact, the same authors, Bhattacharjee et al. From UCSD, proved that certain algorithm can achieve consistency in the robust setting, but they do not provide any convergence rate for their estimators. And this is also an important open problem along this line. And second open problem is that we show that it is possible to achieve a d/n fast rate for adversarial setting. but we require this very limited Gaussian assumption. And it's natural to ask, under what other conditions can we get a similar order of 1/n fast rate? In the standard setting, where there's no adversary, we know that some low noise conditions like Tibakov noise or Bernstein noise is sufficient for this order of 1/n fast rate. It will be very interesting to see if there is an analog of these low noise conditions in the robust setting. And finally, the estimator used in our work is a plug-in estimator. That is, we used an empirical estimator of the population quantity mu and sigma, and plug in into the Bayes optimal, robust Bayes optimum classification rule. But in contrast, in practice, people are using adversarial training. That is, they use some surrogate laws and do and optimize a minimax objective to get an empirical classifier. It is not clear whether the adversarial training algorithm can achieve the optimal rate. And it is also an interesting open problem for future work. And finally, I want to thank a few people that I discussed when writing this work. Kaijun Wang from Columbia, Ken Tsai from Princeton, and Justin Kim from Amazon. And this is the end of my talk. Thanks everyone for coming, and I'm happy to take questions.
Thank you, Chen. I think there's a question in the chat area. Yeah, like basically asking for the intuition behind adversarial SNR's signal-to-noise ratio. I think you mentioned about like hardness, but I wonder if she or she's asking for anything more intuitive.
Yeah, so basically, let me see. Let me plug in figure here. Yeah, just look at this picture. So the adversarial signal-to-noise ratio is essentially saying, let's consider a weaker adversary. It is exactly what we mentioned in the talk as the universal adversary that only perturbs the mean. So the goal of the adversary here is just perturb these two stars closer to each other so that the signal-to-noise ratio gets as small as possible. So essentially, just perturb the means of these two Gaussian distributions so they are as close as possible. I hope this answers the question about the intuition behind the adversarial signal-to-noise ratio.
Cool. And the other question, maybe a small question which I have is basically, you know, what if your model is completely black box, right? In which case you cannot make some of the assumptions I'm assuming you have here. Yeah,
so basically Gaussian identity assumption is very, very strong in our case. Yeah, and it's not a realistic assumption in the real world data sets. And I think it's possible to find some analog of the adversarial signal-to-noise ratio in real world data sets. And this is also a possible future direction. And I think it's very intuitively, it makes a lot of sense that this separation between the two class conditional determines the sample complexity of the adversarial robust learning.
Got it. Okay, cool.